My name is Ogwo of Department of Agriculture and Bioresources Engineering, University of Nigeria, Nsukka. This is a presentation on effects of slope gradient and flow rate on sediment transport capacity of concentrated flow in an erodible bed. Soil erosion is designated as the biggest environmental problems in the world. It is very intense in southeastern Nigeria due to low infiltration rates and high erodibility of the soil in the area. The high intensity of soil erosion in southeastern Nigeria is as a result of the high population density and the land per capita in the area rank among the highest in rural Africa. Soil erosion is a long-term problem that is threatening infrastructural development and agricultural production in the area, which needs to be controlled to maintain crop productivity, reduce sedimentation, and reduce pollution in water bodies. Sediment transport capacity is the maximum load of sediment that a given flow rate can carry. In order to develop a process-based soil erosion models, there is a need for accurate prediction of sediment transport capacity. Sediment transport capacity is influenced by flow hydraulics, sediment size distribution, sediment particle density, slope gradients, shape and roughness. When the actual rate of sediment discharge is less than the transport capacity, there will be additional capacity to detach and erode the soil. But when the transport capacity is exceeded by the sediment load, sediment would be deposited and the sediment discharge reduced to approach the transport capacity of the flow. This work is justified in the sense that accurate prediction of sediment transport capacity is a key to the development of a process-based soil erosion models. Sediment transport capacity plays a crucial role in the physical explanation of soil erosion processes. Therefore, this work will be used to know the effect of slope gradient and flow rate on a sediment transport capacity, of which helps to predetermine erosion prone area if the slope gradient and flow rate of an area are known. The main objective of the project is to determine the effects of slope gradient and flow rate on concentrated flows in an erodible bed. The specific objective is to determine the influence of slope gradient and flow rate on sediment transport capacity by using 40 combination of 5 flow rates and 8 slope gradients. Methodology. The soil sample was sourced from a cultivatable layer of 30 cm depth. The soil sample was air dried and sieved through a 4 mm mesh. The soil sample was packed into the experimental flume layer by layer with the use of wire gauze to facilitate even drainage of the percolating water. Each packed layer was 9 cm to get 4 equal portions, which accumulates to depth of 36 centimeters. After packing, the soil was soaked with water until surface flow occur by using watering can to further reduce the variability caused during packing. 100 liters bucket designed with a tap hung at an elevated platform filled with water was used as the source of water supply to the designed flume. The flume bed was designed with 0.01 mm diameter perforation to create room for infiltration. Concentrated flow of water from the bucket was channeled into the experimental flume with the use of the PVC pipes of 25 mm in diameter, and the concentrated flow enters the flume under gravity. Flow meter was incorporated into the design in order to measure the flow rate discharged from the elevated bucket. Figure 1 shows experimental setup. The experiment lasted for 5 minutes following the initiation of runoff, which was collected in a series of 5 plastic containers at 1 minute interval over a 5 minutes period. The sample was decanted after 24 hours and taken to laboratory for gravimetric analysis. Hydraulic jack was incorporated to the design to enable slope change. Key letter die was used to determine flow velocity. As the fluid moves, the die was sprinkled on the surface of the flowing water at a marked point. Then a stopwatch was used to observe the time it took to cover the distance. Flow velocity is determined as in equation 1. Transport capacity was equally estimated from the concept of transport capacity deficit proposed by Foster and Meyer first order detachment transport complaint equation as in equation 2. Sediment load, rate detachment rate, and detachment capacity were all estimated using equations 3, 4, and 5 respectively. Results and discussion. Figures 2 and 3 show that sediment transport capacity increases with the increase in both slope gradient and flow rate respectively. It was observed that there was always a slight increase in sediment transport capacity for gentle slopes at the range of 5% to 12.1% at different levels of flow rate. The results showed that the relationship between sediment transport capacity of concentrated flow and slope gradient as well as flow rate can be described by power functions with R squared greater than 0.885 and exponential function with R squared greater than 0.843 respectively. Figure 2 shows the effect of slope gradients on sediment transport capacity. We can see that at gentle slopes, there is a slight increment in sediment transport capacity, but the steeper the slope, the more increment in sediment transport capacity. While figure 3 shows the effect of flow rate on sediment transport capacity, and there is a strong response of sediment transport capacity against increase in flow rate than it does against slope gradient. Discussion. These findings are similar to the work conducted by Zayo et al. 2017, of which there was an increase in sediment transport capacity as the slope gradient and flow rate increased. In Zayo et al. 2017, there was a slight increase in sediment transport capacity at gentle slopes of 17.6% and 26.8%, and a marked increase was observed at steeper slopes of 36.4% and above, particularly at a higher flow rate. From their research, it was shown that the relationships between sediment transport capacity of a concentrated flow and flow rate and slope gradient can also be described by power function with R squared greater than 0.859 and exponential functions with R squared greater than 0.714 respectively. In conclusion, concentrated flow in ray channels is one of the transport paths for eroded soil to reach the larger stream network. A faulty combination of 5 flow rate and 8 slope gradients were investigated in this study. Sediment transport capacity notably increased with increases in both the flow rate and the slope gradient, but with flow rate having a greater effect. The results showed that the relationship between sediment transport capacity of concentrated flow and slope gradient as well as flow rate can be described by power functions with R squared greater than 0.885 and exponential function with R squared greater than 0.843 respectively. This is the list of references cited in this study. Thanks for listening.